Hello, my name is Dr. Jim Quigley. I'm Technical Lead for Cargill Animal Nutrition and the author and webmaster of the calfnotes.com website. I want to thank the organizers for the opportunity to be with you today, and I hope that my presentation will, in some small way, help your understanding of young calf nutrition and health. Okay, let's get started. Today I'd like to cover the topic of the first days of the calf's life. I'll discuss how even life in the womb, but also the first week or so of life, can influence a calf's health, development, and even her future performance as a cow. Okay, let's have a look. An important observation made by several researchers in the past 10 years is the realization that early life nutrition and management can influence future milk production of the calf. It's clear that there are many things that influence the milk production of a first calf heifer: her diet, genetics, housing, environment, etc. And how she was fed prior to weaning nearly 2 years earlier won't have a huge effect. However, it appears that the effect is real, measurable, and repeatable. It also appears that, though we initially thought that early milk intake was the main driver for improved milk production, it appears now that growth in general seems to be more important. Therefore, feeding programs, including calf starter, need to be carefully dialed in to optimize growth to weaning. And who knows, perhaps growth all the way to puberty or even breeding could be more important than growth to weaning. Only future researchers will tell us. As I mentioned, I'll address 3 topics today: epigenetics, colostrum feeding, and feeding transition milk. This will not be an exhaustive literature review, as there's a lot of interesting work going on and too much to cover today. I'll really focus on what might have a practical influence on management today. That is, what you might be able to implement on your farms or your customers' farms to help improve early life calf management. I'll also touch on a few new, more theoretical trials to keep things really interesting. Okay, let's go. Back in 1998, I presented a talk in a symposium at the American Dairy Science Association annual scientific meeting. The topic of that presentation was how prepartum management could influence young calves. Little did I know back then that this topic area would explode into an incredibly important area of investigation and application on dairy farms. My title at the time was something like, "What you do to mama, you do to baby." It's still an appropriate title. I don't want to get down into the weeds about the biochemistry of epigenetics. Suffice for today to say that epigenetics is the study of heritable changes in gene expression or cellular phenotype caused by mechanisms other than changes in the underlying DNA sequence. Most mechanisms include DNA methylation or histone modifications that the expression of the gene is affected. These changes in DNA expression are usually permanent and affect offspring in future generations. Interest in multigenerational effects of the environment began during the Second World War, during a time called the Hunger Winter. In 1944, toward the end of the war, the population of the Nazi-occupied part of the Netherlands, especially around Amsterdam, were deprived of food due to a blockade that took place in the winter of 1944 and early 1945. The combination of relatively good medical care and record keeping, along with the calorie deprivation that occurred, resulted in startling realizations about the effects of the hunger winter, not only on the women who were pregnant during that time, but also of their children and their children's children. If a woman was in mid to late gestation during the hunger winter, her children would be smaller, and this reduced body size would pass on to subsequent generations. The children would be thinner than normal, and they would have lower glucose tolerance than their siblings. However, if a woman was in early gestation, her children would tend to have a greater risk of obesity and altered lipid profiles. They would also have higher rates of cardiovascular disease and generally had reduced cognitive function, especially later in life. The confounding issue to scientists was that these changes passed on from generation to generation. Since 1944, we've learned a tremendous amount about how factors affect the fetus. Management issues such as stress from heat or transportation can permanently influence the newborn. Nutrition can influence the fetus too, either in positive or negative ways. It's interesting, but not all epigenetic effects are due to stress on the mom. This is an interesting study in mice where a tremendous amount of epigenetic research is being done, and we're learning a huge amount about the biology of epigenetics. Let's start with an adult male mouse. We're going to expose this mouse to a chemical, acetophenone. It's a chemical used in many flavoring agents, in chewing gum, and in fragrances. It has an orange-like smell. Okay, so we'll give this mouse a smell of the chemical, and then we'll give it a small shock. We'll repeat this until the mouse relates the smell to the pain of the shock. We can tell this by measuring stress hormones in the blood that indicate that the mouse is stressed when he smells the chemical. Next, we'll introduce the male mouse to a cute little female mouse and let nature take its course. Soon, there'll be a bunch of baby mice running around the house, and Mama and Papa are proud parents. Well, if we give the babies a smell of the acetophenone, they'll react in the same way as the father by producing stress hormones, even though they're never exposed to the shock. This effect now passes on to the second generation, likely due to changes in the mechanism of DNA expression. So as we talk today about effects on the fetus, recognize that this area is quite dynamic. And we'll be likely thinking about epigenetic effects on the male, although frozen semen is unlikely to sense too much stress. This is actually one of my favorite studies regarding the epigenetic effects of stress on the offspring. It's actually in pigs, but I think you'll find it interesting. These researchers took pregnant sows and restrained them with a nose ring for 5 minutes a day only during weeks 12 to 16 of gestation. Apparently, sows don't like to be restrained, and they responded by producing stress hormones. But what effect did it have on the piglets? Well, it turns out a lot. Piglets born to sows that were restrained had a greater risk of disease, greater mortality, lower serum IgG, and lower response to inflammation compared to piglets born to sows that weren't stressed. Pretty incredible, I think. But wait, there's more. Well, let's look at cows now. In this study, pregnant beef cattle were either not transported or transported every 20 days from 60 to 140 days of gestation. When their calves were born, these calves were exposed to a glucose tolerance test to see if any changes occurred in their metabolism. As it turns out, several changes occurred, including reduced peak insulin, lower time to baseline after a glucose challenge, as well as a lower insulin area under the curve concentration. All these indicate that the metabolism of glucose as mediated by insulin was different in these cattle, and all because their moms were transported during gestation. In a more recent study, Holstein cows were divided into two groups based on their baseline oxidative status. High OSI is assumed to be a more stressed animal. Well, calves born to those high OSI cows were smaller at birth and stayed smaller until 4 weeks of age. They also had higher amounts of circulating haptoglobin, an indicator of stress, as well as greater amounts of reactive oxygen and nitrogen species, or RONs. These calves were also less capable of responding to an inflammatory challenge, indicating that their overall immune response could have been affected. In another stress study, researchers fed beef cattle diets that met the NRC requirements, or at 70% of the NRC requirements as restricted, from 45 to 185 days of gestation. A third group was fed the same restricted diet, but amino acids were added back to the diet in the same concentration as the control to reduce the effect of low protein on fetal growth. After 185 days of gestation, all cows were put back on the control diet until calving. The calves were born and raised normally until they were slaughtered for beef. In the table, you can see the effect of the diets on the cows here at the top. At the start of the study, cow body weights were similar, but by 185 days, the restricted cows were about 50 kilos lighter. However, due to compensatory gain, by a few weeks prior to calving, all cows were about the same weight with no difference among treatments. Similar responses with condition score were observed. By the end of the period, the restricted cows were thinner, but they recovered by calving. Now let's look at the calves. The calf birth body weights weren't any different, about 39 kilos. The carcass weights didn't vary markedly either, but yield grade, the assessment of meat quality, was significantly different. Calves born to restricted cows had a higher yield grade. The lower numerical value of the USDA yield grade, the higher the expected yield of closely trimmed boneless retail cuts. A yield grade 1 carcass provides the greatest amount of saleable beef, while a yield grade 5 is the lowest yielding carcass. So higher yield grade means less beef or a less desirable animal. Further, the amount of muscle was less, as was the amount of adipose DNA in various fat depots. All of these data indicate that the nutritional restriction of the dam had a negative effect on the offspring and the resulting product produced. Okay, I'll wrap up with a little good news on the epigenetic front. Added rumen-protected methionine to the dry cow diet is thought to provide methyl donors to the cow that may provide precursors for methyltransferases to methylate DNA, RNA, and histones. When rumen-protected methionine was supplemented in the dry cow diet from about 3 weeks prepartum, there were significant effects on the concentration of insulin, the glucose to insulin ratio, and lower concentrations of reactive oxygen species, including greater resilience to stress in the newborn calves. However, there were no significant effects on calf body weight, acquisition of passive immunity, nor in growth or intake parameters. However, these data do suggest that the dry cow diet may be a vehicle for improving the calf's ability to deal with challenges postnatally. The information I've shared here is just a glimpse into the very exciting area of investigation, that is, epigenetics. You'll have more opportunity to hear from others in the program in their research in this area. Not only are the research results biologically meaningful, they're actionable too. It's possible to apply many of these findings on the farm today and save real money for the producer. It's an exciting time to be working in this area. Okay, I'd like to switch gears here and spend some time discussing colostrum. As most of you know, I've been working in the area of calves for many years, and I'm excited to say that these past few years seems like we've had more research and more interesting research in the area of colostrum than ever before. Much of it can really help us manage calves better, improve health and welfare of calves, and reduce the costs to the farmers. Other research is quite theoretical in nature, and in many ways we are still struggling to understand the role of colostrum to the newborn calf. Many laboratories are looking at the effects of colostrum components on things like gut development, establishment of the gut microflora, and expression of genes involved with metabolism and digestion. To date, the practical application of most of this work has yet to be realized. Hopefully, we'll continue to gain an understanding of the role of components other than immunoglobulins, but there's much more work ahead. I'd like to review some of the recent trials that have practical application, as well as some more theoretical studies, and see where this leads us. An important recommendation was published last year in the Journal of Dairy Science by a group of researchers who work in the area of colostrum management. I was honored to have been a part of the working group that developed these recommendations. The discussion around this paper was the observation that while calf mortality in the United States has been declining as more farmers evaluated their calf serum IgG concentrations, there's been relatively little effect of these changes on calf morbidity. The group reanalyzed the USDA NOMS calf study from 2014 and found that we needed to increase the recommended serum IgG concentrations to achieve reductions in calf morbidity. We agreed that the herd level targets made the most sense. So instead of simply looking at individual calves and measuring if the calf had a serum IgG less than or greater than 10 grams of IgG per liter of serum, we need to look at a number of calves on the farm and determine what percentage of all calves fell into 4 categories: poor, fair, good, and excellent. You can see the target serum IgG concentrations here, as well as the standard percentages for the percent of a herd that fall into each category. We can estimate the serum IgG concentration in an individual calf by doing a little math. We take the quality of colostrum times the amount fed. In this example, 50 grams per liter times 4 liters at 2 hours of age and 2 liters at 12 hours of age, and multiply this intake by the apparent efficiency of IgG absorption, which in this example is 45% at 2 hours and 10% at 12 hours. The AEA is estimated from a curve that is similar to data from published studies on the age at gut closure. We then take the amount of IgG absorbed into the bloodstream of the calf and then divide that by an estimate of the blood volume using a somewhat standard estimate of blood volume as a percentage of body weight in newborn calves. The resulting value is the predicted serum IgG concentration that we have traditionally compared to our standard of above or below 10 grams per liter. If an individual calf is above 10 grams per liter, all was good. Given the new recommendations that are based on the percentage in a herd, how do we estimate that percentage in our target for a total herd? We can use a tool called a Monte Carlo simulation. A Monte Carlo simulation is a prediction of an outcome incorporating random variation and repeated many times. Some Monte Carlos are run 1,000, 10,000, or even 100,000 times to get a useful estimate of what the outcome might be. In our case, we can predict the serum IgG concentration of a calf and repeat that prediction many times to incorporate the variation that is inherent in the values that go into the calculation. As a result, we can then estimate the percentage of a herd that falls into our various target categories. To determine the potential effects of colostrum management on herd-level passive immunity, I built a simple Monte Carlo analysis in Microsoft Excel. I used a normal distribution for each random variable with means and standard deviations taken from publications in the literature when they were available. You can see the values I used here in the table. The analysis randomly generated calf body weight, ages at feeding, plasma volume, and IgG concentration of colostrum fed. Each replication was an individual calf with calculation of serum IgG and AEA. Serum IgG concentration was calculated by taking IgG intake times the AEA at each feeding. The AEA was estimated using the exponential decay curve you see in the graph at the bottom of the slide. Please note that this decay curve is hypothetical, as we discussed previously. Although we know that AEA declines with advancing age to gut closure at about 24 hours of age, the actual AEA curve is not clearly understood and is certainly going to vary by individual. However, to keep the Monte Carlo analysis simple, I did not vary the curve from the standard that you see here, with a maximum AEA of 50% and a half-life of absorption of 5.4 hours. The volume of plasma was estimated using body weight of 9%. The analysis was composed of 1,000 replications, which generates a reasonably normal distribution of predicted serum IgGs, as you can see in the frequency graph here in the top right. The average serum IgG in the base scenario was about 11 grams of IgG per liter. In the table on the left, we see the new goals outlined for herd-level serum IgG concentrations. Then, each line contains the inputs of the simulation: liters fed, age at each feeding, and colostrum concentration. Then, the percent of the 1,000 calves that fall into each category for each of the individual Monte Carlo simulations. In the first row, we see that feeding 2 liters of colostrum at 2 and 12 hours of age with 50 and 25 grams of IgG per liter, respectively, will result in most calves below 18 grams per liter. Clearly, we don't reach our herd level goal with this approach. Increasing the feeding to 3 liters in the first feeding helps, but not enough. Even if we feed 4 liters at 2 hours of age with an IgG concentration of 50 grams per liter, we see that we're still not reaching our goal, particularly for calves greater than 25 grams per liter. Only when we increase the colostrum IgG to 75 or more do we achieve the herd level of immunity that we're looking for. If we delay feeding until 8 hours of age, we also see that we don't achieve adequate serum IgG in the highest category. These simulations indicate that, according to the assumptions in the simulations, that we need to feed at least 75 grams per liter of colostral IgG and feed at 2 hours of age. If we feed 4 liters at 2 hours, then we'll be okay. If we want to feed twice, we need to feed at 2 hours and again at 8 hours of age to assure that the colostrum is fed at least 75 and 50 grams of IgG per liter. This simple little simulation might be helpful as we think about herd level recommendations for immunity. There's been a lot of work in the colostrum field recently. I somewhat arbitrarily grouped all of the studies into several categories, including studies with more practical in nature and evaluating circulating IgG, health, and survival of calves. Also, there are some more theoretical studies that are trying to figure out the effects of colostrum or specific components of colostrum on the physiology of the animal, including measures like intestinal morphology, liver protein dynamics, effects on gut microbiota, and on indices of metabolism such as concentrations of IGF-1 and insulin. We don't have time to exhaustively look at all of these areas, so I just picked a few meaningful studies for us to discuss today. I hope I can try to put some of these into context with a bit of classical data. The first study I'll review is one published in 2020 that evaluated different colostrum replacer feeding strategies. Colostrum replacers have been around since the 1980s, when commercial spray drying of colostrum and production of spray-dried bovine serum allowed calves to be fed alternatives when colostrum was unavailable, contaminated with pathogens, or of poor quality. Many studies have evaluated different products in the market, and generally, modern products are valuable when colostrum is unavailable. This study evaluated 3 replacer programs: feeding low-quality colostrum spiked with colostrum replacer, or 2 levels of commercial products. The amount of IgG fed in the 4 groups was 400 grams for the positive maternal control, 154, 150, and 110 grams for the replacer treatments. We can see in the graph several interesting observations. First, calves fed colostrum or colostrum plus replacer had higher initial serum IgG concentrations compared to the 2 products. The maternal colostrum treatment is logical, since these calves were fed more than 2 times the amount of IgG. There was no difference between the 110 and 150 gram treatments, which makes sense due to the variability around measurement of serum IgG in newborn calves. Another interesting observation is that there were no consistent differences in serum IgG concentrations from day 35 until the end of the study. The minimum concentrations occurred at 21 days for the C10, 110, and the C150 treatments, 28 days for the mixture, and 42 days for the maternal colostrum treatment. The calculated half-life for each group are shown here, and tended to be shorter for the 2 products compared to the blend or maternal colostrum alone. These data show that our expectations for passive immunity should be about finished by 4 to 6 weeks of age, when calves having lower levels of passive immunity begin their own de novo synthesis of IgG at an earlier age. Another colostrum study from our group was published back in 2017, but provides some interesting insights into the influence of passive immunity on calf performance. In this trial, calves were fed a colostrum replacer product 3 times in the first 24 hours after birth. Treatment 1 received a total of 150 grams of IgG from the product, that is, 50 grams of IgG per feeding. The second group was fed 150 grams of IgG per feeding, so they got a total of 450 grams of IgG. You can see the difference in circulating serum IgG concentrations on day 1 and each week until the end of the study on week 8. Calves fed the lower amount have lower circulating levels of IgG, only about 4 grams per liter on day 1. Their serum IgG concentrations stayed low until about 4 weeks of age, when their own IgG production kicked in to increase their circulating IgG concentrations. This age is similar to what we saw in the previous study. Calves fed for C450 achieved about 16 grams of IgG per liter, and that concentration declined to 3 weeks of age and gradually began to increase thereafter. So what effect did this huge difference in serum IgG concentrations have on calf health and performance? Well, in a word, not much. In trial 1, we fed 2 levels of milk replacer with the idea that calves with FPT might not grow as well as calves with higher serum IgG concentrations. Well, we were wrong. I won't go over all the numbers, but if we look at the gains, intakes, and efficiency values, we see that both groups did fine, and there were no differences among treatments, except that calves fed more milk grew faster and ate less starter. This doesn't necessarily agree with other studies in the literature that indicate that calves with more IgG are more likely to do well. Well, what's going on here? Well, we wondered that too, but realized that our calves are generally exposed to very little stress in terms of climate, housing, or especially disease challenge. These calves were very healthy, and there were no real differences among treatments in terms of health events. So, to push this idea a little further, we conducted a second study where we fed the same colostrum products, but this time we housed calves on clean or dirty bedding in our experimental facility. The dirty bedding was held over from a previous trial and contained varying amounts of manure and urine from other calves. Again, neither IgG level nor bedding level affected growth or intakes, although the calves on the dirty bedding tended to grow slightly less. If you step back and look at these calves in context, you'll understand that the management of the facility is top-notch, and though the calves were less comfortable on the dirty bedding, they were still not challenged significantly and so grew well. I think this points out the importance of understanding the context of the research. These calves, although they were housed in dirty bedding, were managed extremely well. And trials conducted in highly managed experimental research facilities are likely to be very different than those conducted on commercial facilities, especially if calves are purchased from sale barns or transported long distances. A final thought about replacers. At least some data suggests that IgG from replacers are metabolized differently than those of maternal colostrum. This trial from Murphy et al. Evaluated the half-life of IgG from maternal colostrum or from a colostrum-derived replacer and found that the half-life of IgG from the replacer was about 19 days versus 29 days for the maternal colostrum, shown here in red. I've included the logarithmic decay curves here, so it's a little easier to see the differences in slope of the decay lines. The steeper slope of the yellow line, the colostrum replacer, shows that these IgG were leaving the circulation sooner than the IgG from maternal colostrum. Now, there are many possible reasons for this difference, and for the lack of difference that we've seen in some other studies. We know, for example, that processing colostrum to make a replacer can influence the nature and structure of the IgG. Excess heat can denature the molecules, shortening the half-life. High concentrations of IgG in a product can induce dimer formation, which are then metabolized by the animal, again reducing half-life. Storage of replacers in heat can also exacerbate dimer formation. So there will certainly be some variation among brands of product due to the processes inherent in their sources of colostrum and methods of manufacturing. Also, methods of handling, storage, and reconstitution can also both influence absorption of IgG as well as their half-life. In a very practical study, researchers in Michigan evaluated farm records from the births of over 4,000 calves that were fed either one or two feedings of colostrum in the first 24 hours of life. There wasn't any measure of IgG intake, but we should assume that calves fed 2 times would have higher IgG intakes from the second feeding. And if the second feeding is prior to gut closure at about 24 hours of age, the calves can be expected to absorb at least a portion of the IgG in the second feeding, as we saw in my earlier schematic of IgG absorption. So it's no surprise that 22% of the calves fed 1 time had FPT, that is, serum IgGs less than 10, while only 9% had FPT when fed twice. The impact on farm health was pretty dramatic. The odds ratio or hazard ratios are shown here for 2x versus 1x feeding. So calves fed 2x are only about half as likely to get respiratory disease compared to calves fed 1x. They're only about 1/3 as likely to have diarrhea, and so on. Note that while health measurements were improved, feeding twice did not affect overall mortality, nor on the ages at insemination or at calving. I would point out that overall mortality was only 1.4%, so this farm clearly does a good job in overall calf management. Okay, let's switch gears and look at some research surrounding the effects of pasteurization on the colostrum and the calf. In this study, colostrum was not pasteurized or pasteurized and fed to calves, and the group monitored blood metabolites to see if changes occurred due to pasteurization. They monitored many different parameters shown here: IgG, IgA, insulin, and IGF-1, serum Brix, glucose, and total protein, as well as a snapshot of the serum proteome, a large number of proteins expressed by the calf. The picture on the right is the proteome on all calves on the x-axis by pre-feeding and 8 hours post-feeding of colostrum. The red shows proteins that were higher in the circulation after feeding. We can see that most proteins are higher after feeding, as seen by the large block in the post region. The difference between heated and raw is shown here. The researchers indicated that many of these proteins were likely absorbed from colostrum, which makes great sense, since most of them were found in measurable concentrations in colostrum, and absorption of colostrum components is thought to be nonspecific via pinocytosis via intestinal endocytes. Though the author suggests that these proteins may be absorbed and may be important to the immunity and or metabolism of the calf, it's not clear how long these proteins will remain in the circulation. To understand my point, we're going to jump way back in time and look at some classical research. These research trials, published in 1961 and 71, reported that calves fed colostrum within 2 hours of birth began excreting proteins in the urine in increasing amounts from about 10 to 28 hours of age. Thereafter, the amount of urinary protein, called proteinuria, declined to baseline levels. They reported significant amounts of IgG fragments, FAB and FC fragments of the IgG molecule, which are commonly produced due to papain or cathepsin and pepsin digestion. Many proteins in the circulation at 8 hours are likely to be excreted due to the higher permeability of glomerular filtration that occurs in the newborn. Urine from newborn calves has been shown to contain many proteins found in colostrum and likely represent clearance of these proteins by the kidney. The newborn kidney has a higher permeability of filtration, which allows more and larger proteins to move to the urine. Okay, let's move on to another topic, the effect of heat treatment on proteins in colostrum. It's clear that pasteurization influences the resulting protein concentration of the product. Is this a good thing or a bad thing? This study by Sandana in 2019 suggests that pasteurization is a good thing. These researchers collected colostrum in 3 categories: high IgG, medium IgG, and low IgG, and heated each for 0, 30, or 60 minutes at 60 degrees C. Calves were then fed 3.8 liters by 1 hour after birth. Now let's see what happened. Heating reduced IgG somewhat, and this has been reported by others. Generally, we can expect about a 10% reduction in colostrum IgG content with pasteurization. However, heating also reduced standard plate count, coliforms, and other measures of bacterial contamination. SPC declined by nearly 2 log units when colostrum was heated for 60 minutes. As far as serum IgG, we see that increasing quality increased serum IgG, especially in the heated colostrum. AEA tended to decline with greater quality of colostrum, which is likely due to oversupply of IgG and the calf's limited ability to absorb all the IgG in a single feeding of 3.8 liters. Heating colostrum also tended to increase AEA, especially in the medium group. Taken together, this study certainly supports the value of pasteurizing colostrum prior to feeding. More and more progressive farmers are investing in dedicated colostrum batch pasteurizers to include this valuable job on the farm. Lots of research has been trying to figure out the role of colostral growth factors such as insulin, IGF-1, IGF-2, and other molecules on calf physiology. A research group in Germany has been working on this area for several years and recently published a couple of papers that try to answer this important question. In this first paper, calves were fed colostrum or a formula with a nutrient profile, that is, protein and fat, similar to colostrum. The main difference then would be the bioactive molecules found in the colostrum. In this study published in 2020 by Lehrman et al., they fed calves colostrum or formula 2 days and then milk replacer to 10 days. They monitored concentration of various metabolites in blood and selected metabolites in liver. You can see here the concentrations of serum IGF-1 and leptin. Although colostrum contains a lot of IGF-1, there wasn't any difference in concentration between the groups. However, concentration of leptin was consistently higher in calves fed colostrum. When these calves were fed formula, they had lower protein, IgG, which is to be expected, haptoglobin, leptin, adiponectin, and IGF binding protein 4. They also had a higher urea, insulin, glucagon, triglyceride, and cholesterol on day 1. There were a few other differences. The biological significance of these changes in metabolites is somewhat unclear, particularly the lack of effect on liver activities. This could suggest that at least part of the responses seen in other studies is due to nutritional factors rather than the activity of the bioactive molecules in colostrum. Let's put what we've seen into some perspective. First, the changes in recommendations for herd-level IgG standards will change our approach to recommendations for feeding colostrum to calves. Perhaps an approach such as simulating serum IgG in a herd could help us better recommend feeding approaches to meet these goals on the farm. Next, the recent research with colostrum replacers shows that most products can't adequately replace high-quality colostrum. There's just not enough IgG in a bag of product to replace high-quality colostrum. They're best used when colostrum isn't available or is difficult to administer in a timely fashion. We also saw that calves-fed replacers in achieving lower serum IgG concentrations will generally begin producing de novo IgG earlier in life. The half-life of colostrum products may vary as well, so be sure you know what you're buying in a colostrum replacer. And finally, low IgG is not automatically the theoretical kiss of death. Calves with low IgG can still grow well if they're protected from immune challenge by good management, housing, and nutrition. Certainly, we need to improve our management when calves are not optimally protected by enough colostrum, but it certainly can be done. The recent work on pasteurization suggests that while heating does alter the profile of proteins ingested and absorbed by the calf, the value of pasteurization in improving AEA and reducing contamination makes it a simple decision for most farmers. And finally, new research on how colostrum influences the basic physiology of the calf has produced some interesting findings, but the practical application of most of this research awaits further application. Our final topic for today is transition milk. Let's figure out what makes this so valuable to the calf. I define transition milk here, and I assure you that there are many other definitions in both the scientific literature and the popular press. In any event, we know that it is neither first milk in colostrum, nor is it saleable milk. It lies somewhere in between. And we see that the composition here that changes with milkings after calving. Most interesting are the nutrient content, along with the concentrations of immunoglobulins and other bioactive molecules. I'd point out the concentration of IGF-1, which is about 20 times the concentration of whole milk in first milk in colostrum, but is still very high in transition milk. Before we jump into the bioactives in transition milk, I'd like to look at this as a nutritionist. Let's say we're going to feed 6 liters of milk from each feeding after calving, and let's say that milkings 2 and 3 are fed to the calf on days 2 and 3. I've done some calculations for each feeding here in the table. If we feed 6 liters of first milk in colostrum, we see that we feed 1.4 kilos of solids, 402 grams of fat, 840 grams of protein, and 8.5 megacalories of ME. Although the nutrient content declines with milkings 2 and 3, you can see that the calf is still getting a lot more protein and energy when transition milk is fed. The calf is also getting all of those bioactive molecules that are still found in transition milk also. I want to show you a couple of studies that suggest that transition milk can help reduce the risk of disease in calves. The first is a little older, published in 2014, wherein calves were fed colostrum and then transition milk for 0, 2, or 4 feedings. Calves were monitored for health scores, and we clearly see that feeding transition milk reduced the odds of calves getting sick with nasal or eye or ear infections. However, there wasn't an effect of transition milk on fecal scores or the number of calves with a cough. In the second study, calves were fed colostrum on day 1, then were assigned to be fed milk with the addition of colostrum to create a form of transition milk for the first 14 days of life. You can see that adding colostrum at either 300 or 700 grams per day had a major effect on fever, depression, diarrhea, and pneumonia incidence. It also increased body weight gain and feed efficiency, though we don't know if these responses were due to the immune effects of feeding colostrum or the added nutrition in the mixtures. To answer this question, we'll turn to an older study wherein calves were fed no supplement or a colostrum supplement to provide 10 grams of IgG fed twice per day, or a placebo fed at the same amount as the colostrum supplement and having the same nutrient profile. The calves were monitored for 60 days and health events are recorded every 28 days. The results are clear. We see on the left that adding the colostrum supplement in red reduced the risk ratios for days with diarrhea and days treated with antibiotics. Both supplements improved intake and growth, indicating that the previous growth responses were probably due to increased nutrition. However, health effects, as we see here in the survival curve for treatments for diarrhea, are clearly a function of the colostrum supplement and the health benefits. Although adding colostrum to milk is not the same as transition milk, it does accomplish an important function, providing immunity during the post-gut closure phase when calves can still benefit from a steady supply of immunoglobulins and other proteins in the gut, which is still adjusting to extrauterine life. The next study shows another study wherein calves were fed colostrum replacer at 300 grams per day to provide 64 grams of additional IgG. You can see that the odds of calves being treated with antibiotics or getting diarrhea or respiratory infections were all significantly reduced with the addition of colostrum to milk. This study provided a lot of IgG from dried colostrum, which is probably not economical under all conditions. In addition to bovine serum, other proteins that provide IgG and other immune components, I call them functional proteins, are available in the market, and many of them have been evaluated experimentally. I summarize a few, certainly not all, of the studies using plasma, dried colostrum, and egg proteins as sources of functional proteins. The effects on calf health and growth are shown here in the 2 columns on the right. As we look down the column, you can see that a majority of the studies report a positive outcome in terms of health, whereas few studies report improvements in the growth of calves. It's not clear whether these functional proteins might have the same effect on gut integrity as does transition milk or bovine colostrum, but the consistency of response in terms of calf health suggests that these additives are useful in improving calf health during the first 2 weeks of life. So let's try to put all of this into some context. What you do to mama, you do to baby. That's the bottom line for epigenetics, and it really should encourage us to properly feed and manage our dry cows. Colostrum feeding continues to be the single most important management activity in the calf's life. Greater knowledge on using replacers and the value of pasteurizing colostrum will improve our ability to provide immunity to calves. Although colostrum contains an incredible array of non-IG proteins, growth factors, and other bioactive molecules, the practical value of feeding them is still not completely clear. Transition milk is highly valuable to the calf and should be fed whenever possible. Feeding products to simulate transition milk, colostrum, plasma, or egg immunoglobulin, can provide valuable immune support during the first 2 weeks of life when the calf needs the most help. Well, that'll do it for today. Thanks so much for your attention, and I hope you found my presentation to be of value. I encourage you to stop by the calfnotes.com website for more information on calf health, nutrition, and management. Enjoy the rest of the conference.